This is part 3 of 3 in our discussion about interacting species. We're going to review the mathematical model describing mutualism between two species. This is a scenario in which both species receive mutual benefit from their interactions. A typical example is a plant pollinator system for a mutualistic relationship. So here are the equations. X of t denotes the density of one species, y of t denotes the density or population size of the other species. Very importantly, the interaction terms b x, y, and beta x, y, they appear as a positive, as an addition in each of the equations, and that is consistent with the positive nature of the interaction. So what will be left as an exercise is to take these two equations and repeat the steps that we discuss for the model of competition between two species. Namely, you would like to compute the steady states or equilibrium points, and you would like to specify some cases or scenarios, and then choose parameter values and consider different sets of initial conditions to compute numerical solutions of these equations describing mutualism between two species. And the last example that we briefly derive here to conclude our discussion about interacting species is a scenario in which we have three species interacting. One of them is a predator, here denoted with x. X of t denotes the size of the population of predator, and then there are two prey, that is the y population for prey number one and the z population for prey number two. Some of these expressions are very familiar to previous expressions. Um, we can, well, let's revisit each of them here. So the predator equation has two terms for the gain and one term that is a loss. The first term, alpha x z, denotes the interactions between this predator and the z population, and for the predator that means a gain, is a growth from eating z, and the second term in the gain is a growth from eating the other prey, here denoted by y, and the last term denotes a loss due to mortality by natural causes. For the y population, we have a growth term. This is a very um, similar equation as the original Lotka-Volterra type model, which assumes that in the absence of predator, this y population grows linearly. And in fact, if you consider the ratio dy dt over y, then you're assuming that that stays constant as a positive constant, which is, as we discussed in some of our first lectures, is equivalent to exponential growth. And then there is a loss here for this prey population due to predation. So this is a mortality term due to the action of predators. Now, the Y population has no type of self-regulation, unlike the Z population. This term here, RZ 1 times 1 minus ZK, denotes a logistic type of expression. K is the carrying capacity, and this population has also a mortality due to predation. And it will also be left as an exercise to compute steady states and to compute numerical solutions and to plot these numerical solutions as time plots and in phase plane. Since here there are three state variables, then you could either do a three-dimensional phase plane plot, or you could plot two two of these state variables at a time. You can plot x and y and z, and x and z. And this concludes part 3 of 3 in our discussion of interacting species.